Hello and welcome everyone. Welcome to today's IDEA StatiCa webinar. It will be focused on the application IDEA StatiCa Detail. If you are following our Connection Wednesday webinars, this structure may be familiar to you because last week we were dealing with the steel part of the structure, and today we will show how to deal with this complicated cast-in-place wall in the application IDEA StatiCa Detail. Let me introduce you to today's presenters. My name is Orsolya Kartali. I am a product engineer at IDEA StatiCa, and I have my colleague Lukáš Juříček here with me, who is also a product engineer, and he will show you this example in the application.
Hello, everyone.
During the webinar, please feel free to type all your questions into the question box in the application GoToWebinar, and we will try to answer all of your questions either during the webinar or after it by email. This is a user project from our longtime customer from Slovakia. It is a residence in Ružomberok. The steel part was already shown in a Connection Wednesday webinar, and today we will show this cast-in-place wall in IDEA StatiCa Detail, and we will focus on the anchoring of the steel connections into the wall, as well as the complex solution of this wall example. So please, Lukáš, take the presenter and show the example in the application.
Thank you, Orsi, for a word. So I will take a presenter and hope you can see my screen.
Yes, we can.
Sorry. Fine. So let's do it. So how Orsi mentioned, our today webinar will be focused on the application detail, but we will focus, of course, on the part where are anchored the steel connections or steel joints. So at first, let me introduce the geometry of the wall. So the width is 8.6 meter, and the height of the wall is approximately 6 meters. So at first, I would like to mention or talk about the support. Here you can see that the wall is imposed on the second wall, so we can consider that some stiffness of the wall. We know the height, and we know the equation for the axial stiffness or the calculation of the axial stiffness of the wall. So we will use for a rigid boundary condition, we will use some stiffness which will be inputted to IDEA StatiCa support condition. So I will jump in to IDEA StatiCa and our application detail. And at first, we will create a new project. We will select a design code, concrete grade, reinforcement class. We can let it, and the concrete cover for the detail or the global cover is 30 millimeter. And from the predefined templates, we will use a general input because we will use export from the DXF. So I will run this template, and you can see you have a blank scene, and I will import the geometry from DXF. You can see we have some 2D drawing of the wall, and at first I will click on the line, and by command consecutive I will select the perimeter of the wall, and using outline shape create the geometry. And after that we have to input the opening for a window. So in the same way I will select the line by usage command consecutive, select the perimeter and using the opening shape to create the whole model of the wall. So I will turn over to the real 3D geometry, and you can see how the wall looks. And because we are working in the 2D with the 2D, let's say the 2D problem, so we have to input the thickness of the wall, and the wall has 0.3 meter thick, and it's all for defining the geometry from the DXF. But software wants to me that the structure is statically overdeterminate, so we have to input the boundary condition. So I will use line support from the templates. So, and how I mentioned, it will be a rigid connection. So the RY or the rotation will be fixed, and we have to switch it off this button because this is some it's some compression only spring support. Yes, so I will use it because I would like to have that the support will be acting in the compression and tension as well. So, and by this pen, I will change the stiffness. The stiffness will be 4184, and this support will be placed to the edge 13. Sorry, 13. I will switch it off to the 2D drawing, and by using copy command, select the edge number 3 and finish the process of the inputting the whole geometry and inputting of the supports. So now I will come back to presentation, and how was mentioned, we will focus on the anchoring to the wall. Some from the global project which was created in the Tekla structures, we know how the anchoring looks, and we know the critical combination of the internal forces which will appear on this connection. So we will use the more application to receive the tensile forces in the anchors. You can see, or if you are familiar with our application IDEA StatiCa connection, you can see this is some typical joint anchored to the wall or concrete block, and we will use the analysis from the IDEA StatiCa connection to receive the tensile forces or forces in the anchors. You can see here is some critical combination, and on this picture you can see the status of the analysis from application IDEA StatiCa connection. We received some tensile forces in the anchors, but some problem occurred. You can see that the utilization from the point of view of the concrete cone breakout in the connection is 2000%. So it's a problem. So we have to resolve it in a other way, some advanced check. And this is the reason why we are here, because we will use the application IDEA StatiCa Detail, where we input the reinforcement and try to resolve this problem with the concrete cone. So at first, we have to point it out that we are working in our application Detail. We are working with 2D model, with a 2D model with the real reinforcement. So we have to use some simplification of the model. You can see that we will have, or in the application connection, you have 6 anchors, but how I mentioned, we are working with the 2D model in application detail. We will have only three anchors with the spare diameter of the both from the 6 of all them anchors, right? And the spare diameter is based on the equals on the equal stress in the anchors. To better explanation, here we have a diameter of the anchor 30 millimeter, and this diameter will be 42 millimeters. For the same force, for this force, we have some stress, and for this anchor, we will have the same stress. It's the point. So how to, or what's the approach for simulating for simulation of the transferring the tensile forces in the anchors in application detail? We have to use we have to use some entity or some device for transfer of the tensile force, and it will be hanging. The shear force will be transferred using uniform distributed load on the edge of the wall. So I will come back to IDEA StatiCa Detail application, but at first I would like to show you that we did some analysis for a pure or plain concrete in our application detail, and you can see that the concrete cone appeared here by 15% of the applied loads, right? So without reinforcement, the concrete cone breakout will appear. So it confirmed the claim in the application connection. So I will come back to application detail and create anchors. So I will use a hanging load, and from the shape I will use a lifting stat. So the minimal, or I'm sorry, at first I will start with the defining of the edge. So the anchor will be placed to the edge number 12. The minimal length on the outside, from the outside of the wall, is 0.05 meter, and the total length of the anchor is 80 centimeters, and the spare diameter 42 millimeter. As you can see, so I will come back to presentation. Here you can see that in application connection there are some rectangular, let's say, stiffener in the anchors. So we will use this type of the anchorage, let's say a perfect bond, because we consider that the anchors will be fixed or welded to the reinforcement which will be inside the wall. So the exposition is 15 or 150 millimeters from the top of edge, and for the other anchors we will use a copy command to speed it up, this modeling, and I only change the exposition of the anchor. So the distance between the anchors is 160 millimeters, so 0.32, and the last one, I'm sorry, here is 0.05, and the last one 0.48. Now you can see we arranged the anchors, and we can continue to the next connection. So now we step up to the next connection. The next connection, you can see from the drawing that that is some truss frame, and here are some here is some diagonal with some beam in the bottom, and it's anchored to the wall as well through the base plate. But we received only pure compression force which are transferring through the base plate to the concrete wall. You can see from the analysis we received the forces in the anchors, but the tensile forces was only were only in the two top anchors. The other anchors are under compression. So how to resolve it in application detail, or how to model it? For tensile or tension forces, we can use the hanging, how I mentioned in the previous for the previous anchors or for the previous joint. But how can we resolve the compression stuff? From the connection analysis, you can see this is the distribution of the stress or compression stress in the concrete under this part of the connection. So we can receive from this application, we can receive some average stress. We can receive some average stress, and which is here 6.1 megapascal, and we receive as well some effective area which can be exported to the DXF, and we can receive some area. And if we know area and the stress, we know the force, and we can as well receive the uniform load which will be acting to the left edge of the wall, and the shapes of the uniform loads looks in this way. So I will come back to application detail, and I will do modeling of this part, this connection. So I will create a new hanging load, and the exposition will be 2.99 meters from the left from the top part of the wall. But I know from the geometry that the anchors are without this rectangular plate, so I let it only straight. Okay. So, and for inputting of the load, so we can proceed after that. So I will come back to presentation, and I didn't know if I mentioned that we will focus on the free anchorings. So the third part, or the third joint which will be modeled, is a shear joint. And as you know, the shear joint is transferring only the force, only the shear force, without the bending moment. So and this connection is perpendicular to the plane of the wall, and is visible here. So how to simulate the load from this joint? So we know the shear force, and the shear force will be transferred using a patch load. I will come back to detail and create a new transfer devices as a patch load. So for the patch load, we have to add some effective radius where will be redistributed the force to the area of the wall, or directly will be or directly to reinforcement. So the effective radius will be 0. or 120 millimeter, and the X position is 0.13, and the Z position is 3.2 meter. Now you can see here we have inputted the device for transferring of the load, and it's all for defining geometry, and we can proceed to defining of the loads. So okay, so at first I will name the first load case. The first load case will be a self-weight. I will go through the load impulse and select the surface load. The surface load, you can see what happened. The surface load will be minus 7.5 kilonewton per square meter. So this is for the simulation of the self-weight. Now we can come back to the load case and load combination and create the other one. You can see that this is some non-standard shape of the wall, and here is some notch where is placed the rank where we have to input the load from the rank. So I will name it rank and go through the load impulse, but I will select no surface load but line load. The line load will be placed to DH number 9, and the intensity minus 50 kilonewton per meter. Okay, so now we are going through the first joint. So I will apply the load, or yes, the load, the tensile forces in the anchors from the analysis of the first connection. So I will create a new load case which will be permanent. I will name it joint 1. Go through the load impulses, and using button plus I will select a point load. The point load will have intensity, or the value will be minus 230 kilonewton, but not in the global Z direction but in the X direction. I only copy that and change the force on the 290 kilonewton, but the transmitting devices will be the second anchor. I only copy that and change to the third anchor, and the intensity minus 260 kilonewton. How I mentioned, here is acting as well some shear force, and the shear force will be redistributed through this edge. So I will create a new line load which will be acting in the global Z direction, and just a minute please. It will be minus 18 kilonewton per meter, but it will not be through the whole length of the edge number 12, but only part of edge. And X position, this is from the top side, is 0.20 meter, and the total length of the acting load is 0.3 meter. Now we have defined the load for the first joint, and we can step up to the second joint. So I will come back to load case and load combinations, create a new load case, and of course I will come back to the load impulses and I have to use or input the force from I will come back here, and you can see here are two forces with the intensity 6.2 kilonewton. So the total force will be 12 for one anchor, one spare anchor. So the force minus 12 kilonewton, which will be acting to this anchor. And now we are going through the inputting of the compression load from the analysis in the connection. So I will create a line load, and the intensity of the line load will be 647 in the x direction, and the exposition is 3.05 meter and the length 40 millimeters. You can see. Now I only copy that, change the intensity 1815 kilonewton per meter, the exposition 3.09, and the length is 120 millimeters. And again, I will use a copy command, change the intensity 647, the exposition is 3.21 meters, and the length 100 millimeters. Now I will do the next copy with the intensity 1830, and the exposition is 3.31, and the length 110 millimeters. And the last one, the intensity is 637. The distance from the top part is 3 meters and 42 or 3.42 meters, and the length 40 millimeters. And from the analysis, we received a really high shear force for each anchor. For each anchor, the shear force was 60 kilonewton. So after recalculating and using this type of the load, we redistributed the shear force on the line load with the intensity minus 937 in the global Z direction, and this is acting on the left part of the wall. So the exposition is 3 meters, and the length is 0.45 meter. Now you can see this is the real load which is acting from the anchored connection. So this is the joint 2, and we create a new load case with the joint 3, where we input only the shear force which will go through dispatch load. Sorry, I'll delete it and go through the impulse and input only a point load minus 30 kilonewton in the global Z direction through patch load. Now everything is fine, so I can proceed to demodeling the other load. I'm not sure if I showed you that. I will come back here. You can see that to the wall is junctioned the ceiling. So we have to cover the load or some shear force which is acting to the wall. So we will use some uniform load which will simulate the shear force through the ceiling. So I will come back to presentation to the last slide here. Okay. Now you can see that from the geometry of the wall, there is some a big opening under the ceiling in the wall, and this caused that the shear force or some shear stress is approximately or is decreased due to lower stiffness, and here under full concreted bottom part of the wall is twice time higher. So I arranged the load from the ceiling in this way. So some adjustment. So come back to IDEA StatiCa Detail and create a new load case, which I will call it ceiling. Go through the load impulse and create a line load. I will come back or turn over to 2D model, and we will use the defining by the polyline. So I will edit the shape, and I will input the coordinates of the load. So the x direction of the load will be 13.5. I'm sorry, 13.5 meter. And the second coordinate is 16.5 meter. You can see how I arranged the load. Click OK, but I have to only change the intensity. So we will use a copy command, use edit shape, and change the coordinates. So the first coordinate 16.5 meter, the second coordinate 21.2, and the intensity is 100 kilonewton per meter. And the last one, because here is acting some girder or some beam, so we will use a copy command with the intensity 50 kilonewton per meter. I only edit the coordinate, and the intensity or the first one is 13.5 meter in the x direction. The second one will be 13.5 meter as well, but the z direction or the z coordinates or increment will be 0.7 meter. And this is the process how I defined some type of the load from the ceiling, and we can continue through the combination. So I will create a 3 combinations. The first one will be for ultimate limit state, and the rest of all them will be used for calculating or for code checking of the serviceability limit state. So, but at first I have to arrange or change the partial factors. So for the first one, this is for ULS, it match. So the self weight will have a partial factor 1.35, rank 1.45 as well, but you have to keep in mind that the forces which were applied to IDEA StatiCa connection to the joint were in the design value. So we let it the partial factor as 1. Yes, we will not change it. And for the ceiling 1.45. The problem occur for a characteristic combination or for serviceability limit state where the self weight and the rank and the ceiling we can let it with the partial factor 1, but we have to decrease the load or the internal forces from the or by the joints, and the factor will be 0.75, and this number appeared only from the equation 1 divided 1.45. So I have decreased the load about 35%, right? So this is the process. So I arrange it for all the joints, and for quasi-permanent combination I will do it in the same way. This is some conservative way. So I arranged the load or the load combinations, and for speeding up the process of the calculation, I switch it off the load cases, and I will jump in immediately to the reinforcement, where we don't know how to reinforce this wall. So we have two tools for designing or for some preliminary design, and I will run a topology optimization, and I will give a word to my colleague Orshi, and she will show you some question.
Thank you, Lukáš, also for the demonstration. I would like to ask you a question. This is a little research. How do you deal with the analysis and code checking of concrete walls? So, what is your approach for analyzing and code checking of concrete walls? We have 4 possible answers: A, B, C, and D. A is strut and tie analogy. B, shell models in finite element softwares. C, IDEA StatiCa Detail. Or D, you have never analyzed and code-checked a wall yet. So please choose your answer, A, B, C, or D, and type the letter into the question box so we can have a little overview of our audience. I will give you a couple more seconds. So please pick your answer and type it into the question panel of the GoToWebinar. Okay, thank you very much. Lukáš, can I give the presenter back to you?
Okay, I will take a presenter, and we can show the results of the analysis. So I will use some effective volume of the 40% of the whole structure, of the whole wall, and you can see that some blue areas, these are the tensile areas where we have to put the reinforcement to cover the cracks or yes, some inadmissible cracks and the other factors. So now I can let it to I can let the undrawing to reinforcement. So at first I will use wire fabrics. So I would like to show you that we can let the diameter 8 millimeters and the distance of the eyes or of the distances between the rebars, I let 20 or 200 millimeters to 200 millimeters. I would like to show you at first the results of the analysis when you will use only some reinforcement which is according to reinforcement requirements. So in the areas from the point of view of the ultimate limit state and serviceability limit states, you can see that it's not pass in the areas of the first joint where occur a big cracks and the anchors will be pulled out from the wall. So we have to put some additional reinforcement to cover this problem. So I will arrange other or additional reinforcement. So at first I will use a group of bars where will be 5 bars in a layer. The distance between the bars 150 millimeters. The diameter of the bar 16 millimeter and 3 bars in a layer, and I have to change it to DH number 11. So now you can see what happened. I reinforced the most utilized part of the structure, and the second reinforcement will be around the opening. So I will use entity around the opening. Our software automatically detected the opening and inputted the reinforcement around. So I can let the diameter number 8. I only change the distances between the rebars. I switch it to the topology optimization for better view. So for the vertical and horizontal rebars, I've changed the distances and the anchoring length for on the 500 millimeters. The type of the anchoring, I can let it as a straight. For a diagonal reinforcement, I change the distances 50 millimeters, and the length of the bars will be 3000 millimeters. And if I switch on the topology optimization, you can see that this reinforcement will cover this tension. Some problem can occur in this part of the notch. You can see this is a real huge concentration of the tensile stress. So I will use a copy of the operation group of bars. I will change the number of the edge to 10, and I will change the number bars in the layer. I would like to elongate these bars to the bottom edge, so we will use some position of the edge to some extension at the beginning and at the end. And the last part of the reinforcement will cover the tension in the mid in this part of the wall. So I will copy that again, and I only change the number the number of the edge to 9. So now I have reinforced the wall, and we can proceed to nonlinear analysis. But before that, Orshi will give you some other question.
Yes, thank you, Lukáš. So I would like to ask you another question. This will be about your thoughts of the crack width. So where do you expect the maximal crack width? A, at the area of the anchors near the top edge. B, next to the corner of the opening. Or C, somewhere here in the middle part of the wall. So please pick your selection A, B, or C and type in the letter into the question panel of GoToWebinar. And Lukáš will show you the results of the crack checks. So I give you a couple more seconds. Okay, thank you very much. Lukáš, the word is yours. Please show the results of the analysis.
Okay, Orshi, I will take a presenter. Now, you can see the analyze has performed, and we can see the results of the analysis. All results passed, and we will show some detailed check. From the summary overview, you can see the maximal utilized part of the structure from the point of view of the concrete. This is this part. From the anchorage length, how we assumed that this is in the top part of the wall, where is the big tensile forces in the anchors, and the maximal utilization in the tension of the reinforcement, which is in the corner of the window. So we will go through the detailed check. At first, we will show how looks the stresses. This is the principal compression stress in the concrete, which occurred in the areas of the second joint, where a big or huge concentration of the forces under the base plate appeared. From the point of view of the reinforcement, you can see that the maximal stress in the reinforcement, how I mentioned, is in the corner of the window. Here you can see the stress, or the shape of the stress along the whole rebar. And the third one, the third check or detailed check from the point of view of ultimate limit state is bone stress, where the maximum value appeared on the anchor or by the joint 1, by the anchor, the first one, the top one. Here you can see this is the shape of the force, through the anchor, and you can display, of course, all results for all rebars or all hangings, right? Now we will proceed to code check of serviceability limit state. So from the point of view of the stress limitation, where we can switch it on the long-term and short-term effect on the wall, where we consider a creep. So short-term effect, there is some results where the maximum is on the same place as for analysis of the ultimate limit state. And here we are working with the modulus elasticity, which is coming out from the code, and for the long-term effect, where we consider a creep, so the elastic modulus is decreased about the coefficient of the creep, which is defaultly set as 2.5. right? And you can see that the stress decreased due to lower elastic modulus. And now we are going through the crack. So I would like to show you the answer for a question where the maximum place or the maximum area of the cracks appear. There were 3 points and the maximum crack or the maximum cracks appeared behind the anchors where is the maximal bond stress. So 0.180 millimeters. So the right answer was the A. And now we go through the deflection where we will show that the maximal or this is for a characteristic combination. Deflection is calculated from the characteristic combination where the deflection as a vector is 1.9 millimeter. So it's not so much. And I hope it's all from the analysis. And I would like to point it out some small or some point what you should know about the detail. The detail doesn't cover the analysis of the stability, so you have to solve it in other software in other way. So I have written here some solutions, but I hope you know how to do it. And we of course calculated our wall from the point of view of the stability, and we received that this is the massive wall and the slenderness is smaller than the limit slenderness for the unstable form. All right, so this is the massive wall, and it works. It's fine. So I would like to give word to my colleague Orshi, which will tell you something about the conclusion of all the pros of the modeling.
Okay, thank you, Lukáš, and also thank you for the interesting presentation. So what are the conclusions of today's webinar? One of them is that if the anchoring does not pass in the connection app, you can perform a precise and advanced analysis in the detail application, which considers the reinforcement in the wall to check your cast in situ walls or other concrete details. Advantage of this application is that you can solve basically inexhaustible topology of the connection in the plane of the wall. You can even apply a shear connection which is perpendicular to the plane using the load that Lukáš showed you. It offers a complete solution for walls and complete code checks according to Eurocode, not only ultimate limit state, but also serviceability limit state checks, including crack widths. This was all for today's webinar. Thank you for the attention. Please, after the webinar, fill in our short survey. We are really curious about your thoughts. Were you satisfied with the webinar? And what are the interesting topics for you? You will receive the recording tomorrow. It will be on our website and also on our YouTube channel. You can get a free trial version of IDEA StatiCa at ideastatiCa.com if you want to try the application Detail or any of our other applications. Please check out our resource center where you have a lot of documents, tutorials, and materials about our work. Our next webinar will be next week. It will be a Connection Wednesday webinar, a very interesting one focusing on the Battersea Power Station in London. And the next webinar for IDEA StatiCa Detail will be happening in June, and we will show how to model and code check a pier cap. Thank you for calculating yesterday's estimates with us. Have a nice day and thank you for your attention. Goodbye.
Bye bye.